Hello everybody and welcome back to Nuclear Reactor Physics Lectures. Today we're going to continue discussing how fast neutrons slow down to thermal energies in a typical light water reactor system. And today we're going to answer the question of how many scatters are necessary for neutrons to thermalize. To do this, we'll need to introduce something called lethargy. The lethargy of a neutron is the log of E naught divided by the energy of the neutron, where E naught is the original or often birth energy from fission of that neutron. Lethargy means a lack of energy or the amount of slowness that something has. So naturally our definition means that neutrons that have more lethargy are actually slower and thus have less energy, which thus means that they have experienced more slowing down than other neutrons. You may have noticed last time that when we applied the neutron flux as a function of energy, that we used the natural log of energy on our x-axis, which in essence means that we plotted our flux as a function of lethargy. The neutron flux is frequently plotted as a function of lethargy, both because of how many orders of magnitude over which the neutron energy can vary in a reactor, and because plotting as a function of lethargy means that our 1 over E flux in the slowing down range actually is plotted as a constant value when we plot it as a function of the log of energy. Having a plot for the slowing down flux that is constant as a function of energy is actually very useful because it makes it very easy to see the impact of resonances and other quirks in the system which make this flux not constant. Lethargy is also used in another common metric for nuclear reactors, the EALF. EALF is the energy corresponding to the average lethargy of fission. It may be helpful for us to know the average energy of neutrons that cause fission in our reactor because it really tells us how fast or thermal the spectrum is in the reactor. However, determining the average energy of neutrons causing fission is not always informative because it's strongly biased towards high energy neutrons. For example, consider a system where exactly 1/3 of the fissions are caused by 1 MeV neutrons, 1/3 of our fissions are caused by 1 keV neutrons, and the last third is caused by thermal neutrons. The average energy of neutrons causing fission in the system is just 0.333 MeV, regardless of whether 1/3 or 2/3 of the fission are being caused by thermal neutrons. The EV to keV split of neutrons essentially does not matter if we only calculate the average energy of neutrons causing fission. And that's because the high energy neutrons bias the average energy metric, which makes the metric almost useless. If we instead determine the average lethargy of neutrons causing fission, and then convert that value back into units of energy, it can tell us a lot more about our system. So lethargy is useful for plotting the neutron flux, for developing some other metrics describing a reactor spectrum, and, as it turns out, also for understanding the physics of slowing down. Specifically, understanding how many scattering events are necessary for neutrons to thermalize. Let's say we have a neutron in the slowing down energy range that's undergoing S-wave, or the isotropic scattering, and it's scattering from an initial energy E sub I to a final energy E sub F. The probability of that neutron scattering to the final energy EF is described by our old faithful scattering probability distribution, where alpha, again, is this ratio here. Notice that in this expression, the range of EF values, and thus the range of delta E values, where delta E is the average energy lost per collision, depends on the initial energy of the particle. This makes it mathematically difficult to determine exactly how many scatters are necessary, on average, for the particle to thermalize. Now what would happen if we instead look at the average amount of lethargy gained per collision as the particle slows down? This average lethargy gain per collision is described by the variable xi, or also known as squiggle. Xi is the integral over the range of possible slowing down energies of the lethargy gained by this collision times the scattering energy probability distribution function. Note that this equation is really just a first moment expression for an average, again the average lethargy for a scattering event, and we've discussed this first order concept many times before in this class. If we substitute in the expressions for the final lethargy and the initial lethargy into that previous equation, we get this following equation. Solving this equation will be on a future homework assignment, but after we undergo some mathematical excitement, we can see that the average lethargy loss per collision only depends on alpha. It does not depend at all on the initial or final energies of the particle. So how many collisions does it take for a particle to thermalize? If we define thermal energy as 1 eV and assume that a particle is born at 2 MeV, then we need to gain 14.5 units of lethargy to thermalize. Note that lethargy is unitless, but including units here can sometimes make these equations make a little bit more sense. So thus, the number of collisions to thermalize is simply 14.5 lethargy units divided by Xi. Once we have enough collisions to generate 14.5 of these magical lethargy units, our neutron has thermalized. Now let's finish today's lecture by considering several common materials in a reactor and looking at their value as moderators. We'll look at hydrogen, deuterium, carbon, i.e. graphite, and uranium-238. We'll assume that the hydrogen and deuterium are present in light and heavy water, respectively. The parameters we'll examine include alpha, Xi, the average number of collisions for neutrons to thermalize, Xi times the material's scattering cross-section, and Xi times the scattering cross-section divided by the absorption cross-section. Filling in the alphas, we see that hydrogen has a much lower alpha than the other materials, although deuterium is pretty close, which means that neutrons can lose more energy per collision with hydrogen and deuterium than with the other scattering materials. This is also reflected in the Xi values for hydrogen and deuterium, where we see that collisions with these materials will, on average, add much more lethargy to the particles than collisions with graphite or uranium. And thus, if we get more lethargy per collision, we clearly need fewer collisions to thermalize our fast neutrons. Now what about these other parameters? The first one, Xi times sigma s, is also known as the moderating power of the material. Now a moderator is useless for downscattering neutrons if its scattering cross-section is 0. Neutrons just leak so far out into the system that they're nowhere near fuel, and you have to make your reactor extremely, extremely big to have enough downscatter to thermalize neutrons. So the higher the scattering cross-section, the more compact you can make your moderator and reflector regions in your reactor. The moderating power of light water is very, very high, significantly higher than that of heavy water, and much higher than that of graphite and uranium. But we know that light water really isn't the best reflector, right? Why do people usually consider heavy water and graphite to be better moderators? To see why, we need to look at one last parameter, the moderating ratio. Sure, a material is usually a good moderator if it imparts a lot of lethargy per collision, and if it has a high scattering cross-section, but we also need to consider how many neutrons it absorbs while downscattering, and the moderating ratio does just this. Light water has a significant neutron absorption cross-section, which means that a lot of neutrons die before they can thermalize, whereas the cross-section for deuterium and graphite to absorb neutrons is many orders of magnitude smaller, giving them much more significant moderating ratios. Now, we'll end the lecture today by asking ourselves, which of these materials is the best moderator? Clearly it's not uranium. Uranium was only included in this list to show what poor metrics an absorbing fuel material produces for downscatter. But is deuterium the best moderator because it has the highest moderating ratio? Not necessarily. The light water has a much higher moderating power than heavy water, so if you need a compact system, a deuterium moderator might not be your best bet. So is light water the best moderator? Not necessarily. As we mentioned earlier, hydrogen has a significant neutron absorption cross-section, which gives it a relatively low moderating ratio. What about graphite? Now, graphite is usually cheaper than heavy water, and it's very easy to get big solid blocks of graphite, which can also actually act as a heat sink during accidents or transients in a reactor. But neutrons gain so little lethargy per collision with graphite that they're going to be bouncing around for quite a while. Because these neutrons last longer while they're downscattering, they have a much higher chance of being absorbed by any impurities in the system, such as boron, or by being absorbed by resonances in the fuel. This is a good segue because we'll talk about this resonance absorption in our next lecture. But for now, we'll leave you with the idea that the value of a moderator really isn't just tied to one metric, and different moderators can be the best moderator for different situations.